Welcome back to part 2 of this series on compute unit optimization. If you haven't yet, do watch the previous video because this will not make sense without the previous one. But if you have watched that, let's continue with point number 4. Okay, what else can I find in that code that is weirdly inefficient? Should we go with the obvious things? Yeah, because they start to bother me. So point number 4 is what I would call duplicated code execution. And that can happen in many forms and shapes and sizes. I made it really obvious here by calling the same function several times. And especially I made it a function that is also itself very inefficient. So this here could definitely be improved by making a temporary variable like so. Let memoValid be that very execution, and then only use that every time where we would otherwise use that function. There we go. Same code, except we now need one boolean in local storage, so it adds a tiny bit of compute for that. You know, that one instruction that saves the boolean. But then also we save a bunch because we don't need to execute that so many times. So from our 56k, we would now get down to 41k just by not running this function so many times. So yeah, avoid duplicated code. I mean, duplicated code in software engineering really comes from that you have the same code written twice and you should put it in one function such that it's not the same code there twice. But in that sense, it's don't execute the same code twice if it's the exact same code. So the input parameters are also the same. Then just save the result and use that and not execute the same thing again. Yeah, save the result. And there we also see that this function uses quite some compute because running it one time instead of 3 times gets us down like 15k compute units, which means that the function itself might not be very optimally implemented. And I hinted that when I was developing it, but yeah, let's improve on that thing. And the first thing we see here is, I mean, great that we have this debug log here, but getting rid of that is, I mean, this will save us a lot. Just doing that will already help us because we're literally logging every freaking character. So run it. Without that, oh, that log is so much cleaner as well. And we saved another 5k. What was it before? 41 and now it's 36. Yeah, another 5k saved just by removing logs. So yeah, that definitely goes bye-bye. And we can also make that function more efficient, but that will be the last thing that I will be doing today because that falls in the category of common optimizations of your program logic. I'll optimize this function in the very end because then we know all of the other topics and then I can refer to them. So I'll do this in the end, yeah. For now, let's say the obvious things we did. Okay, cool. Moving on. I mean, I can ask you, what are the obvious things that I'm doing wrong here? And you would be like, oh yeah, this thing. Why do you do that when you could instead just call that function? And I don't know if that function is much more efficient, but at least we don't manually iterate over bytes and, you know, add 1 every time. I mean, that's the manual implementation of the length function. And in most cases, using a function, an already implemented function, is more efficient because it has been tested and optimized better than implementing algorithms yourself. So that's my 5th point, I guess. If there are already implemented function or libraries that do the thing that you need to do, use that instead of implementing it yourself. Unless you have a very special use case and you want to do something else, or you really think you can implement it more efficiently. But this implementation, I think, is less efficient than if I were just to say my memo length is memo.leng, and I don't do that. Now we have a sizing issue, but even there, if I cast it to U64, even that is more efficient then. But I'm not sure, so let's try. We're at 36.1k, and now with that native implementation of the length function, we're at also 36.1. I mean, it looks like it's exactly the same. And maybe that implementation is exactly the same. So, okay, fine. In this particular case, we didn't save anything. That's weird though. I thought we would save something. Just for my entertainment, would we save something if we call it here? Saving this one variable here that we just deleted, if that makes a difference. Doesn't look like it. Creating a variable and using it, we can do for free. Guess why? Because the compiler optimizes that away anyway. If we have a temporary variable, here you also have a temporary variable. Just because you don't write it down explicitly anymore doesn't save you anything. Because again, first of all, you need to calculate that anyway, and then secondly, the compiler optimizes that. Rust is a compiled language, so they do stuff like that. But anyway, then my question here is, why do I need to convert that to U64? Wouldn't it be much smarter to have that max memo size a U size already? Because I mean, it's a small number. We really don't need those 8 bytes. 4 is plenty. I wonder if it was different if my max memo size was, I don't know, 255 and I would make it a U8. I wanted to make a point with data structures here and it's not really working for me. So let's just do a theoretical comparison. Some U8s. And Rust is smart enough to make the I a U8. If I were to go to a higher number here, then it wouldn't let me. Interesting, cool, I like it. If we compare that to the same thing but with a bigger data structure, let's say U64, let's see if that makes a difference. Attempt to add with overflow, yeah, of course. Because Anchor, guess what, uses per default the overflow protection. That's because I'm using Anchor. If I would have native Rust, then it would just overflow and be fine. I'm gonna use overflowing add, because I don't mind if you overflow. And then the same down here, just to be fair, in my compare isn't. There we go. So it's successful again, it's not dying. Let's have a look, compare those two. So the sum of U8s, the sum is different because here we have overflows and here we don't. But the interesting thing is how much did it take? So this is 19224, which is roughly 500 compute, 570. And here we have 0 to 6, which is 600. So 590. Really, it's not a big difference, but it is a tiny difference. The exact numbers would be 594 and here, oh god, I need a calculator. And here 569. Again, not a big difference, but a difference. And my point of this is, if you only need U8s, don't operate on U64s, because this here has 8 bytes, this here has 1. So why would you want to calculate on the entire 8 bytes if you just need to calculate on the 1? In this particular case, for building the sum, yes, we would have needed a bigger number. So the right way to do it would be with U32s in that, or even U16s, I think is big enough. But who really uses U16s? That's a niche thing. I only use U16. Actually, I never use them. Either it's a byte, then I use the byte, or it's a 4-byte thing. I'm just so used to that and I get confused if it's not that way. But for efficiency, actually U16s would make the most sense here. So let's compare all of those. For them, it's also 596. For the U32s, it's also 596. So only with the U8s we really saved something. And again, it depends on this implementation. But the point really is, don't use bigger types than you need. That's also one thing that it says here. Here it pushes U64s into a vector. If you don't need U64s, but U8s are enough, that takes less compute. I wanted to make this point with the state as well. My state really has no reason to be U64s. That should be a byte. So all of those should be U8s. Then also in here it should be a U8. Without those calculations we were at 36K. Let's make it a U8. I don't think it really makes a difference here in terms of compute, but maybe it does. Oh, it actually does. From the 183 to the 0.178. So really just a tiny bit, but it did make a difference whether I'm using a U64 or a U8 for my status flag. It does make a difference. Nice. Okay, so that's my 6th point. Use appropriate types, the smallest ones possible. Of course, if you risk getting an overflow, use bigger types, but in this case, those values will never overflow, right? They will always be below 255. Yeah, speaking of types, where did I do that stupid thing? Oh yeah, that stupid thing. Where I was using them. This is also not particularly efficient because I have the if, else if, else if. I think it is more efficient if I just match that thing for the individual possibilities, and then it complains that I don't have all the possible U8 values here, and that's why I intuitively made that an enum in the beginning. An enum per default, even if it has no stuff in here, uses 4-byte numbers for those. That's how Rust does it. So it's again not as effective, and if I know those are those small numbers, I could cast them here. I mean, it's not nice. The nicer way would be having the enum here, but then no, I want to be as cost efficient and as CU efficient as I can, so I'll have the U8. Ah, this is ugly. Can't that enum have just 1 byte for me? And to match everything, we need have something like this here because Rust. And I don't know if that's more efficient than what we had before with the if. Does it read nicer? Kinda. Like, I wouldn't force you to do that, but it does look a little bit nicer. But internally, it probably compiles down to a similar thing, so it doesn't really make a difference, I think. But fair, we can compare. Fair, we can compare. So before it was 36178, now it is 36178. This makes no difference, but it reads a little cleaner. Again, it probably comes down to compiler optimizations anyway. It's just cleaner code that is written like this. And I tried to do it with an enum to make it even cleaner, but then it gets a bit more complicated and I didn't want that. So not gonna do that. So what did we do here? Yeah, unnecessary. If else, we changed to a match. Does that make a difference for CU? No. Because it's the same thing as here, right? The compiler will probably optimize that away. I don't need that if statement here. Because if it's not valid, then I error anyway, so I don't need that. But will that make a difference in terms of the compiled code and then the compute usage that we need? Probably not, because compilers be smart. So again, we will not see a difference. Still the 36178. Even though in code we saved an instruction of that one check, but it doesn't show up. It's if I write like, if true, the compiler will also be like, well, that's just a pointless statement that I will optimize away. However, it will probably change if I have a different check here. It can't be static because otherwise the compiler is smart enough. So how can I outsmart the compiler is my question now. Memo index, I can use that because that it can't optimize away. So if memo index is not 0, something stupid like that. And my point here is to show that with this, it does make a difference. So like this, an if check doesn't come for free. There we go. It costs just a little bit, but it costs something. We see something change because this, it actually needs to calculate versus this where it knew that this is always true anyway at that point. Okay, good. What else can we optimize? Yeah, I found a nice thing for tip number 7. Avoid unnecessarily cloning stuff. I mean, Rust really likes to suggest that you just clone it. But whenever you clone, first think, am I not doing this right? Am I thinking about this the wrong way? Because you really only want to clone if you really need 2 instances of the same thing. Otherwise, you can work with references. And especially if you're working with loops, then Rust will get a bit annoying with, oh, it has been borrowed before, you can't borrow it again. So you really need to think hard how, like, where the flow goes. But that's the cool thing about Rust. Because of those things, it can be so efficient, because it will only clean up memory if it's not used anymore. But then you as a developer can easily get rid of this efficiency by constantly cloning, just to get rid of the warnings that it can't be borrowed again, right? So in our case here, there is no reason that this function must have its own memo. It can very well work on just a reference of a string. And we can very well here, instead of cloning this thing, just provide a reference. And that will work the very same way. Like literally 2 quick changes will save us a bunch of compute. There we go. Instead of the 36178, we now will need 144, which compared to 178 is a smaller number. I mean, it's not a lot, like it's not crazy to, you know, clone a string, especially if it's not like a huge string, which in our case, you know, a small memo like this, whatever, it's like a few characters. We can clone that, but it's unnecessary to clone it. That's the point. Avoid unnecessary cloning if you want to be efficient with compute usage. Yeah, quick and well-made point. That was the cloning part for number 7. Number 8. What's my tip number 8? I think I'm almost done with the important things. But one more very important thing that is very Solana specific. Working with PDAs. Because this can be a huge inefficiency. That's why I saved it for last, or second to last really. Every time when we use a PDA, we derive the PDA with all those seeds. And not just derive the PDA, which is the one expensive thing that we do, we also find the PDA by finding the canonical bump. So essentially, we run that search until we have the canonical bump. And that costs a lot of compute. I mean, not always do we have to run it several times, only if the bump is not 255, but the bump can be, you know, 252 if we're unlucky. And then we need to do all of those derivations. And that's inefficient, especially because we do it twice. Once here, once here. And doing it once, we don't really get around that because the program does want to check that the PDA is used correctly, that it is actually the canonical bump that is used. So we do want to have that check in there once, but it's enough to do it once, and then we can just save the bump and reuse the bump. And as I said, it doesn't happen for all of the accounts. I think for this one it doesn't happen because that number is already quite low-ish. And what does that depend on? Well, it depends on all of the seeds, right? As soon as we change the seeds a bit, we might get a different bump. So let's check it. And that's again just a client thing. With my memo index of 2, I need 36K. With an index of 3, I need 45K. Why? Well, because probably for this one, the bump is different. And I can just temporarily memo account. Nice. It's a nicer way to get the bump. I used to have to say get something something. That's now way nicer. Thanks Anchor for improving. Just temporarily I log that with a string concatenation as well. Wow, crazy. But yeah, I can afford that. So yeah, there we go. Wow, 252. That's quite a low bump, so we had to search a lot. I think with Member Index 2, it was definitely a higher bump. I would expect 255 or 254. Yeah, 255. So there we use less compute for, you know, deriving the addresses. But let's stay with the 3 for now, because only in that case the optimizations make sense. So that's about 50% of the cases where this applies. But it's good that we do it. We want to optimize, and here we do the whole derivation. Okay, because we can't really get around it. But then we calculated that bump, and we can, and that's good practice, save it into the account. And we need to talk about more good practice about this account later. What was I doing? Oh yeah, saving the bump. This new account now has a bump. I save the bump, And then I can here, for this context, provide the bump. I think it goes like this. I say equals memo account dot bump. Then it takes that value and it doesn't calculate the bump anew, so it uses create program address instead of find program address. And that will help us save compute. So from the 45.6, we get down to, drumroll, 41.2. Saves us compute. For the other one, it doesn't make so much of a difference. If the bump is 255, then it would be 36.7 versus, what was it before? 36.6. Why? Well, we now saved the bump, which takes a bit of compute. So for that, it actually made it worse. But on average, it will make it more efficient, because the ones that have a large bump, like this one with a 252, improves in CU. So it is good practice to store the bump and then use that stored bump. That's why we do that, to save compute units. Also to spread it more evenly, such that no matter which account performs the operation, they all use similar compute. Still not the same, because here they're not using the same. But for this one, they use the same amount of compute. And then it's much nicer to predict, because we saw in one of the previous videos where we, try to request the right amount of compute. If there's less divergence between instructions, right, depending on, what input data, and accounts is part of the input data, if it's deviating more, then it's harder to get a good estimation. So we want to be as constant with our CU usage as we can. And that helps us with that. So that was point number 8, I think, of recommendations for compute optimizations. Storing the bump and not always rederiving the entire address. I mean, we still derive it. I mean, finding the bump every time. I could have done way worse and have the same code up here and find program address up here. Because find program address is a very expensive thing to do. But we do want to do it once, and Anchor does it for us. I want to talk about this. We still need to optimize this. And then I want to talk about Anchor. So those are the 3 things that we still need to do. I know it's been a long video. We're almost done. Just 3 more things. And yeah, now I think is a good time. What we did so far is pretty much go through some best practices of things that you can check off your list to make your program more efficient. Obviously, I can't talk about everything. Right? There are subtle ways how you can make your program more efficient, and there are combinations, like for optimizing this very function. We've already gotten rid of the log, but we can do way more optimizations here, because we see we're using data types that are highly inappropriate. What is that? An option. Why do we need an option to get to that character? Well, because that's how that iterator is implemented. Well, wait, why do we need that iterator in the first place? Why do we use the iterator to go to the ith element when we can just iterate over all the elements? So this can be done way more efficiently. I'm gonna keep that for my own reference here. And I'm gonna now try and implement it more efficiently by getting the character directly of that memo, get the bytes of that memo. Oh, that's what I wanted to write. So now we have the character as a U8. So we can't use those nice functions anymore unless we convert it somehow to a character. Let's see if I can do that. Can I just say CS char? That will already do. So that's definitely one way how to do this. The next way would be I would implement that myself on a bitway logic. Bit operations are usually relatively efficient. Yeah, this is not very efficient, I think. But we will see. First, just by removing it from weird things, iterators and options and stuff, to just bytes. I cast it to characters, which again is not quite the same. I'm losing a bit here because a character is made up of several things, but for my logic it's gonna be the same, because I do then check for alphanumeric. Let's see. So 35.2 versus 36.7. There we go. That is 1.5K compute just by getting rid of this weird iterator and options. And now imagine if we actually needed to use that function several times. We're just using it once. But if we were to use it several times with, different values here, different memos, then that adds up. So you want to be efficient. Can we be more efficient? Can I implement this part more efficiently? And before I would really do that, I would write some tests just to make sure that it also then still works. But we're gonna work on the byte and not the character anymore. And now we will need an SC table. So where's the space? Start with that. Space. Oh, there it is. So space when it's exactly 32. That's gonna be this part when the byte is exactly 32. That's for the space. And then for the alphanumeric, okay, so let's check if it's a number, just so you see my thinking process. It's a number if it's bigger or equal to 48 and less than or equal to 57. 48 and 57, 48 and 57. Then it's numeric. And for efficiency reasons, because it's more likely to be an alpha character than a numeric character, I would put if it's a letter in the top, and I will make a temporary variable make it lowercase, that character, and I do that by logically adding a bit, and I'm adding this bit, because the only difference from a capital A to a lowercase a is this very bit. So that's bit number 6. 1, 2, 3, 4, 5, 6. Wait, this way. Which is 32 or 0x20. And the compiler knows how to, it's all the same. Doesn't matter what I write here. I could write 32. I could write 0x20. It's all the same. So that's the lowercase thing. And then I do the same for the lowercase. Must be, let's say, larger than 96 and smaller than 123. Larger than 96 and lowercase smaller than 123. There we go. And I could still flip it around and return if that's not. But again, I let the compiler do the optimizations for me. And I hope that with this implementation, I'm actually faster or more efficient than this alphanumeric implementation. Let's see, because also I don't need to call that function. So 35205 versus 35190. I could punch out a few compute units. I mean, 15 compute units are 15 compute units. I could make it a little bit more efficient. And if my strings are longer, then it might also be more that I'm saving, right? But Andy, didn't you say that we should use the functions that are already implemented because they're optimized? Yes, I did say that. That was actually point number 2 or whatever in my list. But I also said, unless you optimize it more, unless you are confident that you're optimizing it more. And in this case, with using a lot of bit operations and stuff, I did optimize it more. It's definitely harder to read, so I might want to add a comment of alphanumeric with space. Less readable, but less compute usage. And we're optimizing for compute usage, not for readability. I mean, in this case, probably you would be fine paying those 20 compute more just for readability. I mean, that also has a point, right? Clean code is underrated. You want to have readable code. If you're working on a bigger project, you can more easily afford the compute units than to have unreadable code. So I'm optimizing too much now, I think. But I'm making the point of you can always optimize your code to get out a few more compute. Tickle out that little bit more of compute. Stop it. That's how I tick. Stop it. Cool. So point number 9, optimize your code. Point number 10, and that's really the last one then. Let's talk about this. Because this, not only from a compute perspective, but also just from a general clean code perspective, is ugly as you don't okay, so what's my issue here? Look at it and tell me. If you don't see it, think about it. What's my issue? And I have talked about this in previous videos before. My issue is we have 2 U8s, I mean, fair enough, and then 2 strings. First of all, why is the authority a string? I mean, that's the next thing. I missed that. Sorry, we need to fix that real quick as well. The authority should be a pubkey. Please make the authority a pubkey using the right data types. That comes back to point number, I don't know what it was, 5. Use the correct data types. Don't make it a string if it's a pubkey. Because what you're doing again is that weird thing where you do the encoding of base 58 when really you just want to compare bytes of the pubkey. And you don't want to have like weird string lengths and stuff. Make it a pubkey if it's a pubkey. That also means that you then can equal compare the key and not have to encode it, which is good. And you also want to write it in there, not as this encoded pubkey, but as the pubkey itself. And that will as well save us a bit of compute again. I missed that, sorry, I should have done that earlier. But yeah, let's see. From 35190 to what? 133, almost 7. Pff, what a crazy improvement. And no, it's not because of the pubkey itself necessarily. It was really because of that encoding, and that says it also here, there, that to string encoding is expensive. Just by getting rid of that to string stuff saved us a lot, because we had to do it essentially twice or even 3 times, I don't know. Plus, we are comparing strings against each other where we need to check every freaking character. And now we're comparing pubkeys where we can directly compare the 32 bytes. And pubkey addresses, base 58 encoded, are longer than 32 characters. They're 40 something, 48, 44, 40, something like that. So we're also having to compare more than just 32 values. Here we compare just those 32 bytes. Plus, we're using references and we don't create a string that is essentially, you know, created. So it's like the same point as 0.7 or whatever it was. Avoid cloning. If you don't need to create a string, don't create a string. And all of those things combined make this way more efficient. So yeah, this was probably one of the most important improvements that we could make, is to make that authority an actual pubkey. Plus, it's also so much nicer to work with the data if it's actually the proper pubkey, because otherwise we would need to decode the pubkey if we would want to actually properly work with it and stuff. So that was an important thing that I almost missed. Okay, cool. Having that nice number in the compute units now. Why am I still not happy with the memo account layout? Well, because there are 2 and now 3 fixed length values after a variable length value, because a string can have, you know, variable length, arbitrary length. We limited it with our max memo length, but still it stores 4 bytes for how long the string is, and then the remaining stuff comes at the offset of, you know, depending on how long the string is. So that's not only inconvenient for compute usage, that's also inconvenient just for working with it if we, you know, want to search by authority, you know, get accounts by authority, then that's super inconvenient like that. Way cleaner is to put all the variable length stuff at the back. And it's not always possible, especially when it comes to, you know, when you're upgrading your programs or whatever and have legacy stuff to support. But if you can, put the fixed stuff at the fixed addresses, like starting at 0, then the state. So the state will now always be at byte number 33. I'm rhyming a lot today, I love it. Not even intentional. And the bump will always be byte 34, and that will always be the first 32 bytes. Just way nicer that way. And it doesn't cost us anything just to put that in the right order. But a beginner dev might not be aware of that. I mean, this is called string, this is called pubkey. What's the difference? The difference is that is variable length. And that is not. Yeah, so that's just some things to consider. And I don't think that that makes any difference in terms of compute being used now. I don't think that just changing that around will change compute. It might, but we deserialize the entire account anyway, so I don't think it makes a difference. Oh, it actually does make a difference. It actually makes it a bit worse. Don't ask me why. 4 compute units worse. Do we have an educated guess? Not really. But those 4 compute units I'm willing to pay. By the way, before the authority, actually I said it wrong earlier, there's also 8 bytes for the account discriminator, so you also need to count those 8 bytes. So that's actually byte number 9 till 9 plus 32, and then that's byte number, you get it. But still, it's fixed size before. Anyway, those few computes that we have extra now I can afford, because what we get in exchange is totally worth it. And in the long run, it will allow us to save compute later. Sometimes you need to invest a little bit of compute to then save compute later. And that's also the case with the last topic that we're gonna cover today. Topic number 10, zero copies, which is the last topic from this guide that we haven't covered yet. And we find it under serialization. Here it says, if possible, use zero copy and directly interact with the account to avoid these expensive operations. Now, my problem is I don't really know how to do zero copy in Anchor anymore. And for those 2 instructions that I have already, it doesn't really help me much because I do need the memo. I need the state and I need the memo. So I need to deserialize the entire account anyway. But let's assume I had another function, another instruction called invalidate memo. You know, we have this invalidated state. We also kind of want to use it at some point. Basically, exact same as before, same accounts, signer and memo account. I'm just going to check that I have the right authority. I could put that as a constraint here in the anchor, but I'll keep it like that. A guard for if the authority doesn't match, but otherwise I just set the state to invalidated. That's all that the invalidate memo should do. Let's quickly build this. Then also add the invalidate memo instruction to our transaction. Then we need more compute, of course, because we're now also calling that invalidate memo. But that we can now optimize by not deserializing this entire account, but working on a zero copy. Let's see if I can make that work. Not so nice. It failed. It uses less, but it also failed. So that zero probably doesn't. I'm gonna do a zero memo account. Just has some bytes. Just say data. I don't know. I take the first 64 bytes. That should be enough. I don't want to work on the memo anyway. And you are now a zero copy. I put that in here as an account loader with a zero memo. For now, let's just see if I could get it to work at all. So we compare the 17K with the regular account to an account loader with zero copy, where it doesn't deserialize that account. There we go. 16K. So that's like 800 compute units that we save, except we get an error. Oh shit. Oh yeah, because it's a different... can I have the account loader with an unchecked account? I'm not gonna pursue this any further because this video is definitely long enough. My point is, if I wouldn't need to load the entire account here and would just access that one field of the state, I don't need to load the long memo into memory. I just want to write onto this byte, read this and write this. Then I won't need to deserialize the entire account. So a zero copy is more efficient. I can't be bothered to prove that with my implementation, but you can of course read up on it here. And it is probably easier to get it done with native Rust, which brings me to the last, really the last point that I'm gonna make today. If I would implement all of that in native Rust, it would probably also be a bit more efficient, just because I can be more clear on which checks I need and which checks I don't need. In this very case, Now, for instance, I would really love to have my zero memo account have the exact same account discriminator as my memo account. Couldn't get that to work. I would just not want to do those checks, but you know, the way Anchor works, it automatically does the checks such that the newbies are safe, and don't forget the checks. Also the pros sometimes forget the checks. It's fine, but it's always, you know, it's a security versus like the more checks you do, the more compute you need, and you don't want to just optimize for compute. I said that in the beginning, I'm gonna say it again. Don't just optimize for compute units. You do want your program to function and be secure over be efficient, but then wherever you can, try to make it more efficient. And that's where I'm gonna end it for today. Has been a long video. Goddamn, we did learn a lot though. Should we recap? To have your program use less compute, use less logging, use smaller data types, avoid cloning, avoid string concatenation, avoid logging pubkeys. Oh, avoid encoding pubkeys as well. What else do we have? Avoid deriving pubkeys more than you need to. Like save the bump. Save the bump. Don't run the same code twice if you can store the result. And just generally optimize your program and avoid unnecessary deserializations. I think those were my 10. Maybe I got that a bit wrong and it's fine. There's an entire video that you can watch on it. Yeah, I hope that you learned something. This has been a video that's been coming for a while. Like this is one of those important videos where it's just you want to know that, right? You want to be aware of all of those things, such that you can write more efficient Solana programs. In the beginning, it was like, yeah, whatever. We have enough compute for our transactions. Nobody cared about compute. And now we suddenly get to that point where you want to optimize. And if you look at Ethereum, right, they do a lot to optimize their smart contracts because it just makes it cheaper. And with Solana, we will get to that point as well. We are already somewhat at that point, but it's still quite cheap to execute. But it's just that we hit those limits where at some point you can't do more. And that's why you want to reduce your CU usage. And that's why all that knowledge is so helpful. But I've been speaking enough. I've been working enough. I'm giving myself and you as the viewer a break. And then I will see you back here for one of my next videos. Here's some previous ones. Make sure that you are subscribed, that you like this video. And then I will see you for the next endeavor that we're gonna do here on this channel. Learning Solana development. Till then, bye bye.